Okay. A warm welcome and greetings from IEEE Region 10. The IEEE Region 10 webinar series, IEEE R10Talk, is pleased to invite you for the session on opportunities and challenges of integration of renewable energy in grids. This year, IEEE has embarked on this new initiative, that is the webinar series. Today we have with us Professor Cornelis Kikkert from Adelaide, Australia, and Dr. Tahir Saleem Sheikh from Sindh, Pakistan. The webinar in particular is held in collaboration with Power and Energy Society to celebrate the PES week. The IEEE 10 Talk is a joint endeavor of IEEE Region 10 Industrial Relations Committee, R10 Professional Activities Committee, Young Professionals Committee, Women in Engineering Committee, and Students Activity Committee. The primary objective is to focus on enhancing the awareness on trending topics to the community served by IEEE at large. With this, I would invite Professor Takao Onoe, Conference and Technical Committee Chair of Region 10, to make the opening remarks. Professor Onoe, please.
Thank you, Sanjay-san. Hello and good evening, everyone. My name is Takao Onoe. I'm the currently serving the Region 10 Conference and Technical Committee Chair. I'm very happy to be given the opportunity to providing some comment about the opening of IEEE 10 Talk, the second 10 Talk in the series of new initiatives of Region 10 in year 2021. As Sanjay mentioned, this is a very great opportunities to providing the value of the members to the members inside the Region 10 and worldwide with some seminar series on topical talks. So today's talk is about the renewable energy. That is very important for us right now. It is very, especially topical because we had, last week we had the Leaders Summit on climate with the many country leaders, including President Biden and many presidents and prime ministers from the Region 10 joined and then discuss about reducing the amount of CO2. So the one of the key factor is the renewable energy to utilize some other power sources. So this is very topical, and then we are very happy to have the two premier speakers from the Australia and Pakistan. The professors Cornelis Kikkert from the James Cook University, and then Dr. Tahir Saleem Sheikh. He's the CEO of the United Engineering Services from the Pakistan. So we are very excited having these talks, and then please enjoy the contents of the very cutting edge research and the development activities, and even the several examples. Thank you very much for your kind attention. So please let us start our session. Thank you very much.
Thank you. Thank you, Professor Onoe. Thank you. We now move on to the main agenda. That's the opportunities and challenges of integration of renewable energy in grids. And today we have two very experienced speakers. And the first speaker is Professor Cornelis Kikkert, Adjunct and Associate Professor of the James Cook University and the University of Adelaide in Australia. Both the speakers are widely acclaimed across the globe, and I would start with introducing Professor Kikkert. Professor Kikkert completed his degrees in BE and PhD at the University of Adelaide, South Australia, and joined there as a faculty. He was there for 3 years before taking up the facultyship at James Cook University in Townsville, Queensland, where he continued for 37 long years. During this time, he was the head of the electrical and computer engineering for 7 years, and much of his research has been for electronic instrumentation design, covering from power frequencies, that is phasor measurement units, to satellite receivers. For the last 15 years, he has been doing research on smart grid applications, that is power line communications and etc. Professor Kikkert retired in 2010 and then moved to the Adelaide Hills. Since then, he has been an adjunct and associate professor at both James Cook University and the University of Adelaide. For all this time, he has been supervising theses of students at the University of Adelaide on power instrumentation projects. At present, he is also working on the 4th edition of his own book, Radio Frequency Electronics book, which can be downloaded free from the AWR.com website. Professor Kikkert is a senior life member of IEEE and a fellow of the Engineers Association in Australia. He is passionate about the technology and the need to change our power system to keep the planet safe for our children and our grandchildren in future. Today, Professor Kikkert will speak on electric energy transformation. Interestingly, South Australia is at present having more than 50% of renewable energy. And there are some days where 100% of the power is being supplied by rooftop photovoltaic cells. And there are some other days when 100% power is also supplied by the wind energy. The South Australian system has been kept stable even with major interstate connectors failing or major switchyard fires occurring, or when those transmission lines are taken out for servicing. The talk will cover the need to change the energy grid to renewables, the cost of advantages to the consumer in doing so, the challenges and problems, and how they can be mitigated. Thank you, sir. So over to Professor Kikkert. Sir, you can now share. Thank you, sir. Sir, you are muted. Sir, you are muted. You have to unmute, sir.
Okay.
Yes, sir.
Hang on. How do I unmute myself? Oh,
It's okay now.
yeah. Oh, you've unmuted me? Okay. Can you all hear me?
Yes, we can see and we can hear you also. Thank you.
Great. Thank you very much. I've kept the same title that was originally proposed because it suits very well the integration of renewable energy sources into the grid, the challenges and the opportunities. Let's first of all have a look at the present electricity supply. In Australia, we have what's called the NEM, National Energy Network. And in South Australia, that's connected via 2 links to the rest of the National Energy Network. And that's the Murray link at 220 megawatt and the Hayward link at 500 megawatt. In South Australia, we've got just under 3 gigawatt of gas generation, 3.6 gigawatt of renewables, with another 375 megawatt of renewables under construction, and another 2.6 gigawatt announced. In addition to that, there's 1.5 gigawatt of rooftop PV, and typically 1 in 3 houses have rooftop PV. The total demand is, the peak demand is 3 gigawatt, just over 3 gigawatt. The minimum demand is just 285 megawatt, and the average is 1.3 gigawatt. That'll give you a little bit of an understanding of what is happening here. Oops. In the past, one organization generated power and managed the transmission, and it was coal and gas only. All generation was synchronous generation, large slabs of metal rotating, and there were very slow changes in supply and demand. Consumers did not generate power. There was in the future, there'll be no rotating bits of metal, and the stability will come from electronic inverters. Consumers both generate and consume power. All power is produced by renewable energy, solar and wind, and that's of course very variable, so you need to manage that. We need storage to fill the gaps in the generator to load balance. So let's have a look at 3 different factors which affect this transition. The first one is climate change, and that's the need. For 400,000 years, carbon dioxide levels were below 300 parts per million. Now it's 413 parts per million and rising at 2.5 parts per million per year. As you can see, that's the blue curve there. We have a fixed carbon budget for every degree Celsius rise. Now we're above, we're 1.2 degrees above the 1950 to 1980 average, and that's rising at 0.5 degree Celsius per decade. If we don't do anything, we end up with 4 degree temperature rise by the end of the century and 2 meter sea level rise by the end of the century. We now have significant melting of glaciers and sea ice. There is a danger of positive feedback, and once we have positive feedback, we won't be able to stop it, and that'll make much of the earth uninhabitable. And we've got to avoid that, and as engineers, we've got to take our action in that. The Australian government has been very slow off the mark, and this is the Australian actual carbon dioxide levels. The red curve is the 2018 values that the government calculated. They modified it in 2019 and again in 2020. And this curve there, the orangey curve, is the projected CO2 levels. These are the target levels, the 2 brown curves that the government says they will meet and beat. And as you can see, that won't happen. The curve there is a 50% reduction by 2030. And the other curve there is a 0 by 2050. In order to reach 2 degrees C temperature, limit the temperature rise to 2 degrees C, we need to be 0 carbon by 2040. For 1.5 degrees, we need to be 0 by 2030. You can see none of these targets will do that. And in fact, this is the target that we should be following on the black curve there, which is the target in order to get to the 2 degree limit. You can see there's quite a bit there. At 1.5 degree C rise, the Greenland ice melt is locked in, and that'll cause a 6 meter sea level rise in more than 100 years. If the Antarctic melts, that's 60 meters. And many of the cities that we live in will be underwater by then. At 2 degrees Celsius rise, there won't be any Australian Great Barrier Reef, and we'll have the catastrophic bushfires that we've had in Australia last year. We'll have that every couple of years. All Australian states are committed to no carbon dioxide by 2050, but the federal government hasn't made any such commitment. In South Australia, there's been quite a change, which is nicely illustrated by this. This is from OpenNEM. The brown is the brown coal, where you had a brown coal generator. The orangey bits are gas, green is wind, and yellow is solar. So we've gone from just coal, gas, and imports, which is the purple, to very much smaller imports, a little bit of gas, a lot more wind, and solar. And if we look at, for instance, last year's, the average for last year, from the April 2020 to April 2021, we had 62% renewable energy. South Australia plans for 100% renewable energy before 2030. That will probably happen by about 2023 to 2025, and they're aiming at 500% renewable energy by 2050, which means exporting a lot of it in terms of hydrogen or other things like that. As a summary for climate change, ignoring global warming is like ignoring the oil light on a car. Cheaper in the short term, but very expensive to fix in the long run when your engine blows up. If we wait too long, we may not be able to fix climate change and end up with mass population extinctions. And the coronavirus that we've got at the moment will be trivial in comparison. And that's really a very strong and a big threat. Second factor in the energy transition is the energy costs. If we look, this is a table of figures produced by the CSIRO that I've put in here. Brown coal with just a carbon cost included starts at $129 per megawatt hour to about 180, depending on the usage utility factor you have. And if you include carbon capture and storage, you're looking at 230 to 299. If you compare that with wind and solar, you can see that wind and solar, the renewables, are much cheaper than the brown coal, black coal, and gas, either with or without carbon capture and storage. And carbon capture and storage is not yet mainstream, and I haven't found any plants that on the web that actually work correctly. The cost of emission carbon dioxide pollution will rise enormously to several $100s per megawatt hour, per megawatt hour for by 2050. With renewables, the utility factors will decrease, so that means fossil fuels are really uneconomical. And even at the moment, wind and solar backed up by battery for firming is the lowest cost, the lowest way to provide electricity. The demand varies, and you can get some very funny things happening. In this graph, the blue is the actual demand and the red is the price. On the 12th of March, there was a cable fire at the Torrens Island Power Station at the switchyard, and the electricity price, wholesale electricity price, went above $1,000 from 6 o'clock at night to midnight, 6-hour period. The next day, the price was negative for a long period, and the average price for the day was minus $48. The day after that, the price was even lower, and in fact, the demand got so low that the AEMO asked SA Power Networks to turn people's rooftop solar off, so that in order to keep the system stable. In March, we've had 24% of the time had negative wholesale prices in South Australia with the renewable, because they're very low cost, and the coal-fired power stations don't want to turn off. They can't turn off, so they pay money in order to keep going. And really, this shows that we need more interstate lines in order to actually export this extra energy that we have. This is the plot in OpenNEM of exactly the same. That's the event of the fire. Everything got thrown at it, diesel, gas, and at that time there wasn't much wind. 2 days later, this was the time of the peak demand that the rooftop got turned off. And you can see there's a long period from about 8 in the morning to 5 in the afternoon that the wholesale price was negative. In summary, solar and wind are the cheapest form of electricity. We need storage or demand control in order to enable 100% wind and solar. We can have batteries, pumped hydro, solar thermal, hydrogen, and of course we can also have load management. For instance, there's a aluminium smelter in Victoria which takes 10% of the Australian demand. If we vary the load to match the generator, we actually can control 625 megawatt of power, and that's equivalent to having a battery, and we can run that for more than 150 hours at $2.3 per kilowatt hour. So that's actually quite cheap to run. So the third factor is the reliability and stability. Renewable energy is a lot more variable. We still need to have reliable power on at night or rainy days. To reduce the variability, if we have more interconnections between the different states and the different regions, that would help. In Australia, there's a 2-hour time difference between Perth and Sydney. So the maximum sun at Perth and Sydney do not coincide. So you can actually shovel energy back between Perth and Sydney in order to prevent any duck curve. In North Queensland, it's more sunny in the winter than South Australia or Victoria, so you can actually shovel energy from North Queensland to South Australia and Victoria, and the other way around. So it's really good to match the wind energy, solar and wind between states to match the demand. That means we need more storage and interconnections. There's also a change in load profile as you get more renewables. The top curve there is in 2017. This is at the moment, and the other two curves are in the future. So in the future, we'll get a negative demand at midday unless action is taken. Now, if we have home batteries, they can charge up during the day and discharge at the peak at night, and that spreads the load. In South Australia, the minimum load at the moment is 285 megawatt. The rooftop installations are about the same per year, so we expect zero demand in South Australia within 2 years. And we're probably one of the first countries or places in the world where that will happen. The South Australian government now has the ability to control rooftop PV if needed in order to ensure sufficient stability. So if we look at network control theory, the present system stability is limited by inertia, mechanical governors, ramp rates, and so on. With renewable electronic inverters provide all the power, very different stability criteria. So we need to change the stability equations like swing equation, inertia as a basis for control, and we use parameters like corner frequency, damping factor, the standard sort of classical control theory. And we need to have available reserve power or load. because that's much more flexibility, we're no longer constrained to the mechanical parameters. We will be able to get much better stability. If needed, we can program inverters to behave like a typical turbine, but that's not the best way of doing things. Coal and gas provide power control by running the generator below the maximum power, that's called spinning reserve, and using inertia to provide for fast transient changes and governors to provide for slower changes. If we reduce the output of a wind or solar farm below the maximum available output, that means we can increase the power at will or reduce the power at will. And if we've got smart inverters, we can then have 4 quadrature instantaneous real and reactive power control. Batteries will also provide instantaneous match of generation and load, so we can have a much faster control and much more stable control than we can with fossil fuels. If we look at the agility, coal-fired power station can ramp up 2% per minute. Gas will be a little bit faster, 5 or 8%. A flow battery will do 100% in a few seconds. Pumped hydro, 100% in about 30 seconds. And a lithium ion, 100% in one cycle. So if you want to keep your system stable, you really want to add lithium ion batteries. The Hornsdale wind farm has got 99 turbines of 315 megawatt, and together with the South Australia's big battery will then provide dispatchable power, and that uses the principle of running the wind farm at below the maximum power output. The Hornsdale Power Reserve was a 100 megawatt battery, the biggest battery in the world. It's now 150 megawatt, and you can see that's responding there to a trip of a coal-fired power station in Queensland, and does that perfectly. Home batteries can also do that. Many countries are banning internal combustion car registrations. If all cars are electrical, that will increase the demand by 1.6 times, and that may be in 2040. We'll need more generation, but by charging at non-peak periods, overnight or excess rooftop, will minimize the increase in maximum demand. The way that is done, of course, will depend on the load structure. A Nissan Leaf at the moment, for instance, has got vehicle-to-home grid capability. So that's equivalent to a 40 kilowatt home battery, 40 kilowatt hour home battery. My home would then be 100% self-sufficient. In Australia, the annual demand is about 185 terawatt hours, or 506 gigawatt hours per day. If you want to store, in order to have more than 64%, 76% renewables, you need about 100 gigawatt hour of storage. Snowy Hydro is 350 gigawatt. In Tasmania, the Battery of the Nation's got 3 sites, 37 gigawatt hours each. If we use if everybody's got an electric vehicle and we use half the batteries, that'll produce 608 gigawatt hour of storage. If every home's got a battery, there's got 90 gigawatt hour of storage. So there's no problem in getting the 100 gigawatt hour of storage, and we'll have much more than that. For frequency control auxiliary service, there very little storage is required. For day to nighttime use, a home battery is very suitable. For weather events, you need a little bit more storage, and these are the values that we're talking about there. For network stability, we must match either the power, we must match the power generator power to the load. And this can be done by either changing the generator power or changing the load. For industrial loads, we've talked about the aluminium smelting, being able to control in order to do the demand management. For domestic loads, we can do that too. Hot water heating, change the air conditioner or fridge thermostat settings, pre-call or preheat houses, defer dishwashers, pool pump, car charging, and so on. My air conditioner at home has got a Wi-Fi control. I don't mind giving my electricity supplier the access to my Wi-Fi control so that they can change the thermostat settings, provided they give me a very good tariff for it. All of that requires smart metering and communication to control every appliance. That can be done using Wi-Fi or power line communications inside the house. In addition to that, the energy provider needs to read or control the smart meter. In South Australia, they use mobile phones for that. In Europe, they use power line communications. We can also use the internet. As long as we've got communication, doesn't matter. Let's have a look at two risks. Big risk, the duck curve. Negative demand will lead to overvoltage, solar inverting, tripping, instability, and possible blackouts. At the moment, what's being done to prevent that is to limit rooftop to 5 kilowatt per phase or less, and in some places that prevent new installations. They reduced the feed-in tariff. Last year, my feed-in tariff was 14.2. At the moment, it's 8 cents per kilowatt hour. The demand control, being able to turn off rooftop inverters to reduce the output, is available now. That's required new inverter standards, and that can then relax export limits so that people can actually export more power when it's needed. You can use demand side management to shift loads, etc. Or we can use extra supply to generate hydrogen, etc. Having more interconnection between states is good because it's not sunny everywhere, and we shuffle power between states. Second big risk is capacity shortfall. Coal plants are coming to their end of their life and fail frequently. That the coal plants or the generator plants may fail and be out of action for a long time. We need to plan for fossil fuel exit. We need to plan for increased renewable energy to take up that slack as the fossil fuel depart. The existing transmission lines were built between coal plants and load centers. Solar and wind resources are in different locations, and quite often areas of good renewable resources have poor network connections, and that'll be throughout the world. There's a storage shortfall. 100% renewable generation will need storage, and that takes time to plan and implement. Electrical vehicle charging will increase demands and need to be planned, and rules need to be made for reliable operation. All these are exciting challenges. So in conclusion, the future generating mix will be renewables and storage. Gas and phase will be changed out. The control systems will need to be changed. The networks will have a very different management strategy, from a few centrally controlled coal-fired generators to hundreds of thousands of distributed generators with storage. Uncontrolled rooftop PV will create a negative demand. We need management for stability and low energy cost. All that needs government leadership, suitable goals and changes of the regulations. The lights will stay on with 100% renewables, but the government will need to adapt to the new mix. Ross Garneau in April 2019 said, "I have no doubt that the intermittent renewable energies could meet 100% of Australia's electricity requirements by 2030, with high degrees of security and reliability at wholesale prices much lower than any experienced in Australia over the past decade." And in fact, in South Australia, with renewable penetration is increasing, the wholesale price of electricity has been falling over the last couple of years. If you would like to watch something interesting, I would recommend you watch Clark and Dorr on how the electricity market works, and I've included the YouTube link. And these slides will be available for people to be able to follow those links. Any questions?
Yes, we can have the questions, please, from the audience, from the participants.
We can handle the questions after if anybody's got any.
Keith, this is Lance.
Yeah.
Yeah, thank you so much for the presentation. It's very interesting and also very timely as well, as we can see the gradual rollout of the solar panels and the storage. But one thing is always on my mind is in terms of the overall cost to the residents. Well, they haven't got the connections, because obviously the connection costs will still need to be there to maintain the supply. So I do see that, well, people putting on solar panel have their bills reduced. Even for myself as an example, well, I do have 5 kilowatt. I can see my bill has been reduced, and then I can see that, well, the attractions of using the storage, well, in time to come is going to reduce it further. But what happened to those, well, residents? They haven't, well, got those installed. Well, because, well, ultimately, well, we still need to maintain the connection, well, to the household. And you know that Australia is such a big country that we also need to, well, maintain, well, supply to those. So how does it work out, well, financially, well, for those households that are not able to install the system?
Well, actually, it does work out financially. I've got 14.2 kilowatt of solar panels and a battery, and my total electricity cost over the year for an all-electric house is pretty well zero. What's actually happening with the renewable energy in the past, and in particular in West Australia that applies, where they had very thin lines or single wire earth return lines, for instance, they are replacing those and putting basically independent solar grids on there. And that's actually much lower cost than running and maintaining the transmission line. When somebody puts solar on their roof, you can actually do the calculation and say, hey, it costs 90 odd cents per day for having a grid connection. Is it worthwhile? In my situation, hey, I export 6 times more power than I actually use. So I'm a renewable, my house is a renewable generator. And it still works out cheaper for me to actually have the grid connection than not having it.
Yeah, I can see that, because I do have some friends that they have installed the system early on and they got a much better rebate compared to mine. But nevertheless, I do have a reduction in my bills. And the next thing is, of course, I look at the EV vehicle is coming up, and it will ultimately I need to install the storage so that I maintain the charges for the vehicle. I think that's a trend going to be. Yeah, thank you so much for your presentation.
But you may also be able to use your electric vehicle as a storage battery instead of a home battery. So I think the market for home batteries will take a nosedive as people have electric vehicles that'll be their home battery.
Yep, thank you.
Any other questions? In terms of people using their electric vehicle as home battery, particularly if you've got a charger at work, you drive your vehicle to work, charge it up, drive it home, and then use the electricity.
So there's a question in the chat. So battery storage of rooftop energy could be quite expensive. How can it be managed cheaper by net energy metering from grid supply?
Oh, okay. It's very hard to hear your question because you were breaking up. If at the moment in South Australia or in Australia, it costs about 5 cents per kilowatt hour, levelized cost of electricity for your rooftop PV. And I pay 36 cents per kilowatt hour for any power that I consume. So you can see it's quite economical for actually supplying power that otherwise you would use, and it's got a good payback period. My system, I did the calculations, was 3-year payback period before I installed it, and I've just paid off my system in exactly 3 years. The utilities, by the way, the utilities are recovering their cost. If I get power from the grid, it cost me 36 cents per kilowatt. If I export power to the grid, I get 8 cents per kilowatt, which they then sell to my neighbor for 36 cents per kilowatt. So they make a profit on that. Oh. There is one question about the voltage for electric traction, 25 kV, 50 hertz. Normally, the inverters, certainly the inverters in Australia, they're designed for about 230 volt, which is the voltage in many places. And you then have to have a transformer to turn that up to 25 kV or whatever voltage you'd like to supply connected to the grid with. The commercial inverters, like the ones at the Hornstel Power Reserve, would have a much higher voltage. There might be 11 kV to 33 kV, which is the voltages used in Australia. And but of course they won't tell anybody what they're doing. think that's all the questions that I could see.
Prashant, somebody has raised a hand. Asif Jahanjar.
Yes, sir. I messaged him, sir. There is no question from him, sir. Maybe it's by mistake. I think there's no further questions.
I think we can move ahead if there are no questions.
Oh,
Professor
hang on,
Kikkert?
I can see one.
Okay, okay.
Can we provide base load from solar PV in utility scale power plants through costly battery? Yes, you can have base load, and even though the battery is more costly than the PV, the solar plus the battery is going to be cheaper than trying to build a new coal-fired plant, gas plant, or things like that. Right, solar, wind, and battery are the cheapest form of providing basically base load power at the moment. But you wouldn't call it base load, because base load is a power station that you can't change, like a nuclear power station. And in Fukushima, they had the problems with that they couldn't turn it down quick enough, and that's why it melted.
I think we can move to the next speaker.
Yes, thank you, Professor Kikkert. Thank you very much. Thank you. We now move on to our next speaker, Dr. Saleem, Dr. Tahir Saleem Sheikh.
Yes, I am here.
Dr. Tahir Saleem Sheikh is a qualified senior electrical safety and power quality engineer, having experience of 45 years in industrial sector, including 20 years in consultancy wing. He is presently the CEO of United Engineering Services, an electrical consultancy firm situated in Karachi, the capital city of Sindh province in Pakistan. Today, Dr. Saleem Sheikh will cover power quality issues and smooth operation of the grid, which is very important and central to integrated power system. The consequences of poor quality can be catastrophic, leading to economic losses or at least life cycle damages. The methods for getting best power quality are implemented separately for each cause of bad power quality, like separate power supply feeder for harmonics producing loads, surge or deep absorbers for voltage surges, and etc. His lecture will address the introduction of power quality, its importance, assurance of best power quality. Dr. Saleem's talk is expected to be a perfect foil to Professor Kikkert's speech. Thank you, and over to Dr. Saleem.
My practice. So my presentation is visible or not? It's okay?
Yes.
Okay. My name is Tahir Saleem. I am an electrical engineer. And the power quality issue is the most neglected part of electrical engineering. Nobody cares about it. Everybody says, I need power energy, that's all. And the result is that there are so many problems because of this poor power quality, because of poor design. So let's move on and see what happened. My presentation would be, the first part would be the general observation about the power quality, how to improve, and then the second would be the harmonics, its impact, its losses, and whatever it may be, and how to solve this harmonic distortions. In renewable energy also, you need this power quality phenomena very carefully. You have to adopt this power quality phenomena very accurately so that you can, as per IEEE 60034, you need a power of plus minus 10% tolerance limit. And as per IEEE 61000, it will give you the distortion limits, and the frequency would be plus minus 2%. So like a mineral water to for your healthcare, for the healthcare of your power electrical units, you need a quality power within these limits, frequency as well as voltage. And this, your sine waveform should not be disturbed. So let's move on and see what happens. Yes. So there are so many phenomena in power quality: the voltage dip, equipment sensitivity, voltage unbalance, solution for voltage unbalance. I will tell you, flicker and its sources, effects of voltage fluctuations, harmonics, its effects, and solution. So we will see what happens. Electrical power is perhaps the most essential raw material used by commerce and industry today. It is an unusual commodity because it is required as a continuous flow. It cannot be conveniently stored in quantity, and it cannot be subject to quality assurance check before it is used because it is invisible. So you have to check yourself with the parameters. There are some limited statistics available on the quality of delivered power, but the acceptable quality level as perceived by the supplier and the industry regulator may be very different from that required or perhaps desired by the consumer. The most obvious power defects are complete interruption, blackout, which may last for a few seconds to several hours, and voltage dips or sags, where the voltage drops to a lower value for a short duration. Naturally, long power interruptions are a problem for all users, but many operations are very sensitive to even very short interruption like dips or sags. A few examples for the sensitive operations are continuous process operation. If I have the plant which has the continuous operation, a slight sag or dip will disturb the whole plant. Multi-stage batch operation, when interruption during one process can destroy the value of a previous operation, the whole plant may stop. Data processing, where the value of the transaction is high, but the cost of the processing is low, such as share and foreign exchange dealings. So what do mean by power quality? A perfect power quality supply should be one that is always available, always within voltage and frequency tolerance, that is plus minus 2% for frequency as per IC code and plus minus 10% for voltage. And as a pure noise-free sinusoidal wave shape, just how much deviation from perfection can be tolerated depends on the user's application, the type of equipment installed, and his view of his requirements. A voltage dip is a short-term reduction in a complete loss of RMS voltage. It is specified in terms of duration and retained voltage, usually expressed as a percentage of nominal RMS voltage remaining at the lowest point during the dip. A voltage dip means the required energy is not being delivered to the load, and this can have serious consequences depending on the type of load involved. Voltage sags, a longer-term reduction in voltage, are usually caused by a deliberate reduction of voltage by the supplier to reduce the load at times of maximum demand, or by an unusually weak supply in relation to the load because of the load shedding. What we call it is a load shedding. General cause, there are two main causes of voltage dips: starting of large loads, transients because of the large loads, either on the affected side or by a consumer on the same circuit, and faults on other branches of the network. Dips caused by large loads, when heavy loads are started like large motor, welding, and so on, such as large drives, the starting current can be many times the normal running current. Since the supply and the cabling of the installation are dimensioned for normal running current, the high initial currents causes a voltage drop in both the supply network and the installation. The magnitude of the effect depends on how strong the network is, that is how low the impedance is at the point of common coupling, and on the impedance of the installation cabling. Dips caused by starting currents are characterized by being less deep, much longer than those caused by network faults, typically from 1 to several seconds, a tenths of seconds rather than less than 1 second. One solution for this voltage dip is to have a soft starter in circuit. This will drive, your drive will run on a ramp, and there will no much voltage dip on the system. And that solution is to negotiate within the supply company for a lower impedance connection. In our country, we don't have this concept, and this no utility can give you a low impedance connection. Equipment sensitivity. Characteristic of equipment sensitivity: electronic equipment power supplies, such as those used in personal computers and programmable logic controllers, PLC, employ a reservoir capacitor to smooth out the peaks of the fault, full wave rectified waveform. So they should be inherently resilient to short duration dips. The larger the capacitor, the greater the difference between the stored capacitor voltage and the minimum required for the internal voltage converters to operate, the better the resilience will be. Designers will always try to reduce the size of the capacitor to a minimum to reduce size, weight, and cost, by ensuring that the charge stored is just sufficient at minimum voltage and maximum load. For good dip resilience, a much larger capacitor is required, at least twice as large as to enable the equipment to ride through one cycle, and 100 times as large if 1 second ride through was required. An alternative design strategy is to keep the minimum input voltage as low as possible to maximize the hold-up time of the system. The hold-up time will be much greater with a 230-volt supply than it will be with a 110-volt supply. Variable speed drives can be damaged by voltage dips and are usually fitted with undervoltage detectors that trip at 15 to 30% below nominal voltage. Induction motors having inertia so that they may help to support the load during a short dip, regenerating energy as they slow down. They become a generator. This energy has to be replaced as the motor re-accelerates, and if the speed is reduced to less than 95%, it will draw nearly the full startup current. Since all the motors are starting together, this may be cause of further problems. Relays and contactors are very sensitive to voltage dips and can often be the weakest link in the system. It has been established that a device may drop out during dip even when the retained voltage is higher than the minimum steady state hold-in voltage. The resilience of the contactor to dip depends not only in the retained voltage and duration, but also on the point on the waveform where the dip occurs, the effect being less at the peak. A three-phase power system is called balanced or asymmetrical. If the three-phase voltage and currents have the same amplitude or phase shifted by 120 degrees with respect to each other, if either or both conditions are not met, the system is called unbalanced asymmetrical. International standard, for example, European standard 50160EN or the IC 1003X series, give limits for the unbalanced ratio of less than 2% for LV and medium voltage system and less than 1% for HV measured as 10 minutes value with an instantaneous maximum of 4%. However, this limit can be locally reduced even as low as 0.24% to 5% at the British side of the channel tunnel. The first and the most basic solution is to rearrange, redistribute the loads in such a way the system becomes more balanced. For certain applications, there is a possibility of reducing unbalance by changing the operation parameters. This you can do yourself. In order to reduce the influence of the negative sequence currents causing negative sequence voltage on the supply voltage, low internal system impedance is required. This may be achieved by connecting the unbalanced loads at a point with higher short circuit level or by other system measures to reduce the internal impedance. Another type of mitigation technique is the use of special transformers, such as Scott and Steinmetz transformers. Finally, special fast-acting power electronic circuit, such as static varistor (VAR) compensator, can be configured to limit the unbalance. These are expensive devices and only used for large load, for example, arc furnaces, when other solutions are insufficient. VR capacitors are used on the transmission lines. Flicker, it is a symptom of voltage fluctuation which can be caused by disturbances introduced during power generation, transmission, or distribution, but are typically caused using large fluctuation loads or the loads that have rapidly fluctuating active or reactive power demand. The primary cause of the voltage changes is the time variability of the reactive power components of the fluctuating loads. Such loads include, for example, arc furnaces, F-rolling drives, etc. In general, loads with a higher rate of change of power with respect to the short circuit capacity at the point of connection to the supply. It is very important to note that small power loads such as starting of induction motors, welders, boilers, power regulator, electrical saws and hammers, pumps and compressor cranes can also be the source of flicker whenever the transient will occur. Voltage fluctuations in power system cause several harmful technical effects, resulting in disruption to production process with substantial cost. However, the physiological effect of flicker is the most important because it affects the ergonomics of the production environment, causing operator fatigue and reduced concentration levels. Electric machines, voltage fluctuation at the terminals of induction motor causes changes in torque. The torque will vary, and there will be the humming sound in that and slip, and consequently affect the production process. In worst case, they may lead to excessive vibration, reducing mechanical strength and shortening the motor service life. Voltage fluctuation at the terminals of the synchronous motor and generators give rise to hunting and premature wear of rotors. They also cause changes in the torque and power and increase in losses. Static rectifier. The usual effect of the voltage fluctuation phase control rectifier with DC side parameter control is a reduction of power factor and the generation of the non-characteristic harmonics and interharmonics. We come to it later on. In the case of drive breaking in inverter mode, it can result in communication failure and consequent damage to the system components. Electrolyzer. Both the useful life and the operational efficiency of electrolyzer equipment can be reduced in the presence of voltage fluctuation. Also, elements of the high current supply line can become significantly degraded, thereby increase maintenance or repair cost. Operational efficiency of all heating equipment is reduced in the presence of significant level of voltage fluctuation. For example, an arc furnace would require a longer melt time. So, this is a simple introduction about the power quality impacts and what type of the power quality is there. Now we come to the harmonics, which is the most typical and difficult to rectify because it will be costly for you to do some install something to reduce this harmonics level. So we have to be ourselves within the limits of the harmonics. We will see what happens over there. Harmonic is a generalized term used to describe the distortion of a sinusoidal waveform by waveform of different frequencies. Non-linear load changes the sinusoidal nature of the AC power current and consequently the AC voltage drop, thereby resulting in the flow of harmonics current in the AC power system that can cause interference with the communication circuits and other types of the equipment. So this diagram which will disturb by harmonics, the harmonics will create frequency multiple of the base frequency. These harmonics current also lead to increased losses and heating in numerous electromagnetic devices, motors and transformers. When reactive power compensation in the form of a power factor improvement factor is used Resonant condition can occur that may result in high level of harmonic voltage and current distortion when the resonant condition occurs at a harmonic associated with non-linear loads. Now, common source of harmonics is all linear loads. All non-linear loads in power system include power electronic converters, arc furnaces, induction furnaces, static VAR system, inverters for distributed generation, AC phase controller, cycloconverters, AC DC converters, rectifiers commonly used in switch mode, power supplies, and pulse width modulation PWM motor drives. The effects of harmonics in a power system are pervasive in that they influence system losses, system operation, and system performance. Unless the harmonics are controlled to acceptable limits, as described by the IEEE and IEC standards, the power equipment, and even more so, the electronic equipment may be damaged, resulting in costly system outage. The effects of harmonics are due to both current and voltage, although current-produced effects are more likely to be seen in day-to-day performance. Voltage effects are more likely to degrade the insulation and shorten the life of the equipment. The following are some of the common effects of harmonic: increased losses, pulsating and reduced torque in motors, rotating equipment, premature aging due to increased stress in the equipment, increased audible noise from rotating and static equipment, misoperation equipment sensitive to waveforms, substantial amplification of current and voltage due to resonance, communication interference due to inductive coupling between power and communication circuits. I have so many examples in my country where these phenomena happens. Most power system circuit elements are primarily inductive. Therefore, the presence of shunt capacitor used for power factor correction or harmonic filtering can cause cyclic energy transfer between the inductive and capacitive element at the natural frequency of the resonance. At this frequency, the inductive and capacitive reactance are equal. In practical electrical system power factor correction, capacitors are primarily utilized to offset the power factor penalty imposed by the utility. In Pakistan, it is 0.9. This can create an abnormal situation because the combination of the capacitors and inductive elements in the system can result in either series or parallel resonance or a combination of both, depending upon the system configuration. Usually, parallel resonance occurs more often because capacitor banks are in parallel with system impedance. Inductive, this can be a matter of concern if the resonant frequency happens to be close to one of the frequencies generated by the harmonic sources in the system. The result of a series resonance may be the flow of an unexpected amount of harmonic current through certain elements. A common manifestation of the excessive harmonic current flow is an aberrant relay operation, blown fuses, and overheating of cables. The result of a parallel resonance may be the presence of excessive harmonic voltage across the network elements. A common manifestation of excessive harmonic voltage is capacitor or insulation failure. Because managing harmonic in a power system is considered a joint responsibility involving end users and system owners to operate, harmonics limits are recommended for both voltage and currents. The acceptable voltage dissociation level from the basis of the harmonic voltage limit is the figure on the next slide. The recommended limits in this clause apply only to the point of common coupling and should not be applied to either individual pieces of equipment or at a location within a user's facility. In most cases, harmonic voltage and currents at these locations could be found to be significantly greater than the limits recommended at the PCC due to the lack of diversity, cancellation, and other phenomena that tend to reduce the combined effects of multiple harmonic sources to levels below their algebraic summation. Now, this is a standard for harmonic limits in IEEE standard 5192 and 2014. You can see this chart. This gives you of different environments, and different environments, the harmonic limitations are different. So this is the voltage distortion limits, but coming to this slide, we will discuss this, but this gives you a complete phenomenon. The typical environment is what is the acceptable limit for computers and power sources. So what should be the line frequency tolerance limit? whereas the plus minus 2% as per IEEE 60034 and plus minus 10% is the recent voltage tolerance limit, power source tolerance low. These are the different figures. You can check it out over here. So the transient pulses, ground current, how much should be the ground side, the leakage current, maybe the voltage deviation, how much different environment we are using electronic sensitive equipment. So the 0 to 2% total RMS, 0 to 10%, 5 to 10% largest, and generally we will come to that slide over there. 5% maximum total voltage regulator signal circuit is the solution for that. Now this is the IEEE standard 5192014, which give a different voltage level and what to the individual harmonics limits. Globally, there are multinational companies that set their limits as per IEEE and IEEE standard. So for the total the voltage harmonics, the limiting value is 5% and the current harmonic is 10%. THD value, which is called the total harmonic distortion. So high voltage system can have up to 2% THD where the cause is an HVAC terminal, whose effects will have affluent and points in the network. The future users may be connected. Current distortion limit for a system rated 120 volt through 69 kV. This is IEEE standard 59201 for recommended current distortion limit. So you have to operate either as a renewable energy or conventional energy within these limits, so avoid any defects in the equipment. Maximum harmonic current distortion, what should be there? So at this is the ratio given over there, distortion in present of IL. So give you the chart. Maximum harmonic current distortion percentage of IL, total current distortion limit for system rated high voltage, for high voltage. Harmonics order limit 25% of value given in table 2, table 3, and table 4 for that particular standard and codes. Now, as per IEEE standard 61002-4, they have electromagnetic environment divided into 3 classes: class 1, class 2, and class 3. And this class applies to protected supplies and as component levels, though in public networks. Class 2, this class applies generally to PCC and IPCs in the environmental industries. And class 3, this class applies only to IPC in industrial environment. So if I tabulated this in this way, the compatibility level of harmonics, different harmonic level, and the easiest one is that the class 1, class 2. So total harmonic distortion should not be more than in class 1, and class 2 it should not be more than 8%, and class 3 should not be more than 10%. So you have to arrange your non-linear loads accordingly as per design to reduce this level, so that no special, corrective equipment need be required to operate. So this is the class 1 65%, class 2 is the 8%, class 3 you can go through the presentation and find out what covers the class 1, what covers the class 2, and what covers the class 3. So this we have discussed it out: harmonic distortion, blackouts, under and over voltage dips and surges, and transients. Now I come to that, that's different solutions simultaneously. The capacitive reaction decreases, the frequency increases. A relatively small percentage harmonic voltage can cause a significant current to flow in capacitor circuits. Presence of harmonic current causes distortion in waveform. If the natural frequency of a capacitor bank power system reactance is close to a harmonic, then partial resonance occurs with the amplified values of voltage and current. The elevated current will cause overheating. Possible solution, maybe one of the easiest solution is oversize component by 1.3 to 1.5, increase insulation level, and then third would be the harmonic factor, which is the and reactors, which is the costly affair. In generators, if you are operating generators, there would be thermal losses, effect of sequence components, voltage distortion, line notching, and generators. Transformers will have a thermal losses, unbalanced distribution, transformer and neutral current. And for selection of the transformer in environment of harmonic distortion, you have to calculate the K factor. This is called the transformer de-rating or K factor for transformer. And if you are ordering a transformer for a harmonic dissociation environment, then you can have this K factor calculation and find out what should be the K factor and select your transformer accordingly. Induction motor, again, in this, the thermal losses will increase, effects of harmonic sequence component, an explosion-proof motor, and voltage distortion. If you have an induction motor of certain temperature classification, T1 to T6 are the classification for hazardous area, then if you use this in such an environment where the temperature, this will destroy the sleeves of the motor, and the temperature classification will change and will not become a hazardous area motor. So you can see over here in explosion-proof motors, they are designed on pure sine base. You order it. The rotor may overheat due to harmonics resulting hot rotor and damage of seals, and temperature exceeds the T class. WXD, WXC, WXV, WXN, according to EN 60034, 2% voltage distortion is permitted. 3% voltage distortion is permitted for WXN as per EN 60034-20. So you have to be very careful when you are using your equipment in exposure to atmosphere. The environment will have too much effects on these components. A voltage harmonic cause extra losses in the direct line connected motor. And for VFD, the fifth harmonic create a counter rotating field, whereas the seventh harmonics create a rotating field behind the motors. Synchronous speed, the pulsating torque causes wear and tear on coupling and bearing. General use of the increased use of VFD creates this type of a fault for induction motors. So there were so many other effects also: variable speed drives, lighting, flicker, effects of line notching on lighting, potential for resonance, uninterrupted power supply, computer and computer-based equipments. Thermal losses, skin and proximity effects, neutral system in 4-wire system, additional effects associated with the harmonics, effects and negative consequences, conductor or overheating skin effect, depending on frequency, capacitor failure, faulty operation of fuse and circuit breaker, increased stray losses in transformer resulting increase in iron, copper, and eddy, increased losses in generator, multiple zero crossing effect, the timing of the voltage regulator, causing interference and operation stability, incorrect recording by utility meter, that is very important, misoperation of drives, interference in computer and telephones. Now, this is a certain, you can see in this example, the harmonics are increased by 42% and the losses increased to 17.73%. That's why the thermal losses increase in the cable. Sometimes the cable bursts. I have seen that. So with very big plants also. So I have seen this, the bursting of the cables. Measurement, you can have a problems in measurement, peak factor, peak value, form factor, RMS measurement is based on an average reading, and whereas this will have a misappropriation reading to your meters. Measuring equipment, telephone, circuit breaker, fuses, relays, noises, stripping of fuses and relays, radio, audio and video equipment, capacitor. Even I have seen in certain hospitals the harmonic creates so many noises stripping and image distortion in ultrasound labs. So you have to correct this thing. If you come to an ideal power quality, that this is a picture taken by us, our spectrometer, that says that the power quality, the above is the voltage and the lower is the voltage line of current, and THD level varies 1.4, 1.3 and 1.2, 6.9, 7.3 and THD 6.8. So this is ideal and this is a defective operating at the FD. And you can see over here, the power is not much, but the current harmonics is 36.5, 37.7. And the third phase, there is some problem in connection. So I will not discuss 37.7, but it gives you 37.6. This is very high. Normally it should be not more than, if as per global standards, should not be more than 10%. If the environment is very critical for power electronics equipment, it should be more than 5%. IC 600 frequencies which are not integer of the multiple frequencies, they are called subharmonic, whose frequency is less than the fundamental. We will not discuss in this presentation about the interharmonics, but they also create problems in interharmonics problems. So now, what are the linear loads? Resistance and induction motors. Non-linear loads may be induction furnaces, variable drive. We have discussed it earlier, speed drive, solid state, soft state, instrumentation, computer, and so on. This is are the non-linear loads which disturb the power factor. And this is the example of different base frequency is taken is 50 Hz. So harmonics are represented frequency, multiple fundamental frequency. Harmonics are designated by the harmonic numbers of multiple frequency. And you will see total harmonic response is calculated as the sequence of all harmonic divided by the normal frequency. This gives you the formula over here. Now, the one solution for this is to increase your power equipments. So in this case, there is a transformer which gives you 10% THD voltage excess. And if you increase the size, it will reduce to 2%. And generally, it is a general practice that you should not increase a non-linear load on a transformer or a generator more than 20%. This yields RMS value of distortion as percentage of the fundamental frequency. This condition is called a non-linear load, a non-sinusoidal load. The total amount of harmonic will determine the THD of the non-linear load. The more sources impedance, the more voltage distortion. Generally, in general practice, the allowable limits of current voltage, so many global multinational companies have set its limits. The voltage harmonics is 5% and current harmonics as 10% is the best maximum limit. Otherwise, we have to go for that. So these are some of the basic solutions for that. The basic solution is the position the non-linear levels upstream, up remotely from the source. This figure gives you Z1 is the impedance for non-linear loads and Z2 is the sensitive loads. So we have to place them. There will be, you have to decide with the spectrum of the harmonic solutions, harmonic spectrum. What solution is your the best? How much to invest in this? That is your own decision. So this is the one solution that you position your non-linear loads upstreams, then group the non-linear loads. That is, the non-linear loads, you will have a separate bus bar for non-linear loads and for separate bus bar for sensitive loads. This is a general phenomena. You will have a separate source. The third would be that you have a separate source for non-linear load and linear loads, which I've seen in Karachi, a problem in a foundry. In a foundry, I have found with the induction furnace this phenomena. They connected this non-linear load as linear load, a single bus bar. The source is 11 kV, the medium voltage, and there's a lot of problem for that. So they have to separate this source of power, the ME network, with two sources. They have to do it. And then the non-linear will have a separate panel and linear load will have a separate panel. These are the split transformer. I have seen that, but in spite of the fact there is a lot of problem. DYD connection suppress 5th and 7th harmonic, which is the important phenomena generating from a VFD. DY connection suppress the 3rd harmonic, which is the important phenomena for a UPS, and a DZ5 connection suppresses the 5th harmonic, 5 and UPS, both, whatever it may be. So you can see the UPS in positive direction gives you the harmonic current, a 3rd harmonic. The 3rd harmonic means the multiple of the base frequency. 5th harmonic as 7th harmonic means the multiple of the base frequency. Yes, this is also very mostly people install in our country the filters, but forget about the earthing because all this noise level have to go to the grounding. So there would be 3 networks are recommended by the standards and codes in all over the world: TT, TNC, and TNC and IT. So TNC will represent a neutral and ground common phenomena in the distribution network, and TNS will have a neutral and ground separately from the source. The source will be neutral and ground will be the same. The source will be connected. And apart from that, if you're going further, the TNS will have a separate earthing circuit and TNC will have a combined effect. So the power circuit, we will recommend the power circuit TNC is normally recommended, and TNS for harmonic suppression is recommended. And for critical load IT, where the neutral is not earth and the IT and the single fault will not trip your circuit breaker, and the IT and the second fault occurs double fault, the IT breaker will be tripped. So there are certain limitations. So you should have a good grounding for surge protector as well as harmonic distortion limitations. So a filter, if you install a filter, this is very expensive. So its filter would be, what filters are, you can see over here. This is a passive filter. The reactance and capacitance is connected to nonlinear load, and this nonlinear load noise is filtered out through ground, and the pure sine wave goes to the linear load. This is a passive filter, and in industrial installation with a set of nonlinear load representing more than 200 kVA variable speed drives, UPS, etc. This installation requires power factor correction, installation where voltage distortion must be reduced to avoid disturbing sensitive loads, installation where current distortion must be reduced to avoid overloads. Active filter. This active and hybrid filters are very expensive. For nonlinear loads of less than 200 kV installation, current distortion must be reduced. The simplicity is that a nonlinear work type of third, fifth, seventh, 11th, whatever it may be, generates linear. A counter in opposite phase, this harmonic generation unit create the harmonics level, which nullify the impact of the one phase and second and cross phase, and give you a simple noise-free linear load and simple sinusoidal waveform to lower linear loads. So this is called an active filter or sine filter also. This is very expensive. So principle, this is the simple waveforms over here. And this installation is more than 200 kV, a hybrid filter. It is a combination of active sine filter as well as passive filter. The combination, whatever remains with the active sine filter, this hybrid filter will correct them with sensing device to create the same harmonics, and which will nullify the impact of the harmonics on linear loads. So this is installation more than 200 kV. Harmonic, and whenever you have to decide, harmonic audit will determine the exact method. You can say anything. Non-linear should not be more than 20% of a transformer or generator. This is the general practice. And the harmonic collection, they give different harmonic calculation. You can do it over here. This is an example of harmonic calculation. You can do it yourself manually, but the soft starter and the software, whatever it may be, ETAB or Equidate, whatever it may be, they use the direct harmonic dispersion coming out of the distribution circuits. You can use that. This way example. Transformer short circuit current, transformer full load current, generate. These are the different harmonic calculation. Now I come to the conclusion. Power being an important commodity must be supplied to the consumer with best quality as much as possible, so that unwanted distortion in the supply to the equipment is prevented. Poor power quality is not only damage the equipment, but also it interrupts the whole operation of the workplace. The solution for maintaining power quality are expensive, but they can be implemented subject to cost versus output ratio. In textile sector, your product disturbed, the product quality disturbed. So there are so many things. I have seen in a hospital, they built, which is a very big hospital, they built an ultrasound lab. The images were disturbed because of the UPS third harmonic. We analyze it. The third harmonic create noises which create disturbed noises in the patient's images. So what was the conclusion is that the UPS was without a built-in filter. So they connected it to another UPS and the problem was solved. This UPS was without a built-in filter. So whenever you install a UPS for this type of a harmonic distortion, you have a built-in filter or install a separately filter of whatever type you may be required. And proper earthing, whatever I have said is TNS, means neutral and ground cable should be separately run across the whole distribution company. The immediate discharge, I have seen the Navy, in the Navy also, in the dockyard also, they convert this, this is one example, they install a generator and motor to convert 60 hertz to 50 hertz and the whole board electrical power system disturbed due to the VFD stored in the boat. So they have to change it with the 50 hertz and no need. So say they have a radar system in that the boat and they have to change it to 60 hertz radar system. So these are the one of problem. The solution for the meeting power quality are expensive, but they can be applied subject to cost. You have to see yourself. But in our country, I have seen the industrial sector is most negligent on this issue. So they have a lot of problems in this of the harmonic distortion. And sometimes the motor burns, transmission line burns, and AIA, automatic AVR burned of a generator, you have a standby generator. So you have to be very careful in giving the power energy to your equipment. So these are the certain filters installed in the power plant. You can see this is an analyzer over here, different types of analyzer. So thank you very much for giving me an opportunity for this presentation. So if any question arises, I am ready to answer here.
Thank you, sir. We will just have a few minutes for the questions. Let the questions come. We can share with you.
So there's a few questions here. The first question is, how would the third harmonic distortion caused by the single phase motors and the rectifier supplies, other users and the current balance in grid can still use 3.5 crore cables for 380 by 415 volts, 50 hertz, 3 power 4 volts distributed systems?
In fact, it depends on the motor power rating. And you have to, how would be third harmonic distortion caused by the single? What is the question? What is the question?
Prashant, I would
the
request
question
you to
is-
kindly repeat your question because the sound was distorting.
Yes, so the question is, how would the third harmonic distortion caused by single phase motors and rectifier supplies affect other users and current balance a grid?
Yes, it can affect the direct other grids also. So you have to correct accordingly. The most important phenomena in this, the easiest, the simple way is to connect with the TNS system so that it can absorb mostly all the noise levels and the distortions in the ground.
Continuation, sir. Continuation of this, can we still use 3.5 core cables for 380 by 415 volts, 50 hertz, 4 watts distributed system?
Yes, you can use it. But the size of the cable depends on the rating of the motor. A single horsepower 3.5 is enough. Even the 2.5 is enough. But
Okay, sir.
if the environment is harmonic distorted, so you can increase the size of the cable. So that will nullify the thermal effect, the thermal heating of the cable. The impedance will be low if you increase the cable sizes and the thermal heating will be less.
Yes, sir. Thank you, sir. There is another question, sir. Are static wire?
Go on, please. Go on, please.
Yes, sir. Are static work compressors suitable for grid voltage imbalance?
I would the harmonic description.
Are static work compressors suitable for grid voltage imbalance?
Could not understand your question. But
The question is,
static
I'm making it clear. Are static works, HVCs, suitable for grid voltage imbalance?
yes, they are used in transmission line. When CR on the transmission and DIR are installed at different levels of the transmission line for high voltages.
Okay. Prashant,
So
any further questions can you see?
So the final question, sir.
Yes.
The specified distortion limits of 5 by 8% are for rated current and what duration? Are higher limits applicable for short duration?
It's applicable for everywhere. Duration will be the long run as well as the small one. You have to limit this within that limit. 5%, 8%, 10%. This is the IC code, and IEEE also give you. So globally, you can reduce yourself have to limit itself to 5% to 10%. There is no limit to duration.
Sir, one final question, sir. A tuned LC filter has to be connected across 25 kilowatt supply for electric transition to improve power factor by draining out third harmonic. When periodically rectifier locomotives were in service, initial solution of PFA failed due to overheating of capacitors. What would be the situation?
So you have to increase your capacitor size. There are the capacitors available with resonant circuit. So they will reduce the resonance also. And other solution is to you increase the capacitor voltage and capacitor size. So they will solve your problem. Instead of 400 volt, you can go for a capacitor of 500 volt. Instead of 20 microfarad, 50 microfarad, you can go for 75 microfarad.
Sanjay sir, the questions are done.
Yes, I think that's okay. Thank you, sir. Thank you very much. Thank you, Professor Saleem. Thank you.
Thanks a lot. Thanks a lot.
With this, we come to the last and final leg of today's webinar. And we have with us Dr. Nirmal Nair. And I would request Dr. Nair to kindly propose the vote of thanks. Dr. Nair, please.
Thanks. Can you hear me, Sanjay? Hello?
Yes, yes.
Yeah,
yes,
okay.
yes, we can hear you. Yes.
Okay, then. Thanks. First of all, I would like to thank all the attendees of this 10 talk, which has been organized by Region 10. So first of all, thanks for coming to this session. And I have a few people to thank, but I'll first start with the speakers themselves. So the first is Professor Keith Kikkert. And he basically talked a little bit about how his country, Australia, and particularly his region, South Australia, is undergoing an energy transformation, and they're going for higher penetration of renewables. And he mentioned something about solar and wind, and with increasing penetration that way. The opportunities and challenges which he did were mostly around markets, electricity markets, the cost of electricity, retail electricity in his jurisdiction. And there was some interesting discussion about as the transition goes, there will be a little bit of challenges about how do you handle energy poverty, how do you handle essential services of the grid, and things like that. So I think that is just the flavor of all those countries in the world which are going through these energy transformation towards renewable. So I think Professor Keith kind of outlined that in a practical context about what it was, but I think he ended with an optimistic note that it is going to be 100% renewable, and you can operate a system with 100% renewable. which we have to look at how it can be economically done and how it can be securely done. So those are two different aspects. And he brought in the elements of storage and inverters and things like that, which would all have to be faced by the energy operators. So I would like to acknowledge his insight, and also that gives you a flavor of IEEE. IEEE in particular looks at technologies which are going to come in the next 50 years, right? So I think he set us a challenge for all those power engineers and other engineers to watch the space. So thank you, Professor Kikkert. And there is a special memento, as you can see on the screen. I next move on to the next presenter, Engineer Tahir Saleem Sheikh from Pakistan. And I think this was an interesting presentation about an engineer who has been in the field for 45 years. And he talked about voltage quality, even though we call it as power quality. I think he started with some of the key attributes of what needs to be supplied from viewpoint of acceptable power supply to consumers, as well as PCC points and things like that. So I think he set the tone. It was a great tutorial coming through the basics all the way through to the techniques, the mitigation methods, and I think he spent a lot of time on the harmonic side, but then he quickly brought into the flavor of IEEE, which is the standards, right? So I think standards is a key part of IEEE. And as you can see in the acknowledgement, it is PES Day. So he's coming from Power and Energy Society expertise. So that was really interesting to see. But also he brought in some practical context about what can be done and his experiences about the challenges of mitigation, the expenses back again to power quality and things like that. But most of them were load centric. But I think if you kind of put that with Keith's presentation in the future, these establishments would have to look at how to allocate with solar inverters, battery inverters, and things like that. Even though he had some stories about some of the aspects around UPS and how people try to cut cost with buying cheaper UPS, but you can't do that in a sensitive application like a hospital, for instance. So I think it's an intermix of the interaction between capacitors and inductors and the exchanges of power systems, which is basically electromagnetic in nature. So that was neatly kind of tied about, and I think that was a good flavor about IEEE itself, which is practiced by industry people. So once again, thank you, Engineer Tahir Saleem Sheikh, on behalf of IEEE Region 10 and on behalf of PES and other societies which are supporting this part. So once again, a small memento on behalf of us. It's just a mug, and I think some special memento which will be posted to you. Lastly, but not the least, I would like to thank Mr. Sanjay Kar Chowdhury. He was the moderator for this session, and also he has been in the industry for quite a long time. He's now come to volunteer for us as part of Region 10, and he is the industry chair, and he's trying to bring a flavor of the industry chair, even though during these troubled times, which is his country in India and all across the world people are facing. But it was great to see him organize this panel. And interestingly, also Region 10, even though he's the industry IRC chair, I would like to give a shout out to all the other chairs. I think there is professional activities chair here, and I think young professional and women in engineering and things like that. So I think this is a new tone for bringing in all these organizations together to give reflections across the Asia Pacific region. And so I would like to thank Sanjay for pulling all this together in a virtual format. So I think I have finished all my thanks, I think, Sanjay, or is there anyone else I need to thank? Oh, yes, of course. These are the people, as I mentioned, Sanjay Kar Chowdhury, Professor Prakash Lohana from Region 10 Professional Activity, Akila Vijayatunge, who's managing this webinar coordinator. There was some hiccups. I hope you can apologize for us from the panelist side, but I think we had an interesting talk. And also Ashwant for the graphic design, whatever you're seeing on the screen, and the publicity notice by him, by Mr. Hisham, also a graphic designer, and Kanita Tukachamakaran, I think I got it right, the tech leader from content editor, Renu Guntar, also a content writer, and Sai Prashant for the webinar technical arrangement. I think everything has jumped to. I'm here in New Zealand, as you can see, so it's a wide spread of countries which are participating here. So these people together represent IEEE Region 10 Industrial Relations Committee, IEEE Region 10 Professional Activities, Young Professional, Women in Engineering, and Student Activity Committee all put together. So once again, thank you for your patience. I think we are at the end. There is a feedback, and I think it was in the chat window. If you could just flick that, that will be appreciated. So hopefully we would do one of these Region 10 talks in the coming months as you go through. But before I end, I would like to acknowledge, stay safe and be kind to each other. And I hope we should ride through this this pandemic, ravaging pandemic again, and hopefully, all of you get vaccinated soon, and we might meet in the coming few months or years, in person. So with that, I think we'll close this session, and I'll pass it on back to Sanjay if he has some parting word. Thank you.
I would request all of you to please stay back for a moment. We have a photo session, and would request all the panelists and all those who are present to switch on their video cameras so that we can have a group photos. Thank you very much.